Good morning, Math HL students. For our remote lesson 4, we're going to look at a few more differential equations with closed form solutions. Closed form solutions means the solution is of like a known function. It's not a numeric solution. It's not a table of numbers. We'll just look at a few more. There's, as I said, you can fill 2 university level classes with different differential equations that you can solve in a closed form. And we already looked at 2. I'm going to introduce 2 more today just to kind of get you a sense of the different types of things you can solve. And I think after that we might move to applications. All right. Okay, so if you remember, there's ordinary differential equations, there's partial differential equations. Partial differential equations are a pain, and you have to have Calc 3 to do these. So we're only looking at ODEs, which means there's only one dependent variable. One independent variable, sorry. And then the order of a differential equation is the highest degree of a derivative. All right. And then I promised you that there will be more classifications, and there are. So the first classification is linear and nonlinear. A linear differential equation means the dependent variable, the y, is never multiplied by its derivative, and then it's you never like take a square root of it, or you'll never see like sine of y. So it's more technically, the differential equation appears in this form. So you have a function of x times y, a function of x times y prime, a function of x times y double prime, and then a function of x times y to the nth derivative. Notice you never even multiply y by itself. So if this were a y squared, this wouldn't be a linear equation already. And then you might have like a constant term plus a function of x equals 0. This is called a linear equation. It looks like a polynomial. That similarity is explored later on. You can solve these by treating them as polynomials. Okay. And then if it doesn't look like in this form, then it's called a nonlinear. And then we know from algebra and algebra 2, nonlinear is harder than linear. Like if this were squared, it would be different. Or if it said sine of y, or if y prime was multiplying the second derivative instead of just being added, okay? And then, all right, if b of x is 0, if there's no function of x by itself, the equation is called homogeneous. Not homogeneous? I don't know. Homogeneous? I'll say homogeneous. Differential equation. Okay. So that plus bx term also makes it a little bit trickier to solve. Okay. All right, and then we talked about separable differential equations, which can appear in a lot of different ways, but the idea is you can separate the y terms, right? The y terms from the x terms. The linear differential equation appears in this form, the derivative of y with respect to t plus a function of t times y equals a function of t. So this is a linear equation because y doesn't multiply itself, and then it's non-homogeneous because you have that g of t term. And then you remember the steps of solving linear differential equations. You introduce something called an integrating factor, and then you multiply, you use the properties of the product rule. Okay. All right, so we're going to look at 2 different types of equations you can solve, quote unquote, by hand in closed form. And then, all right, and then we'll look at applications later on. But, all right, so the new type of differential equation, and I told you, it's very rare that you can solve a differential equation in a closed form. That's why they have special names, just because most of them you have to solve numerically. So you have to learn how to program a little and write a program that solves them. And then just plot the points and get your curve as your answer. All right, so this type of an equation is called a Bernoulli. I think that's pronounced Bernoulli. Bernoulli equations. And it's, okay, it's y prime plus p of x times y equals q of x times y of n. Okay, well, if n is 0, if there's no y of the nth derivative of y term, then okay, hold on a second. If n is 0, this is a linear equation, right? Yes, if n is 0, this is a linear equation. If n is 1, this is a separable equation, because you can move the p of x times y term to the right, factor out a y, divide by y. Okay, so to be called a Bernoulli equation, it has to be in this form, and n cannot be 0 or 1, and n can be any real number. Okay, all right, and then it's named after Jacob Bernoulli. There's a family of mathematicians, Swiss, I think. Yes, maybe. With the last name Bernoulli. There's a bunch of them. Multiple generations, too. So there's a few things named Bernoulli in math. This one's named after Jacob Bernoulli. And I thought this was kind of interesting. This is an excerpt of his letter. So they discuss things in letters to each other. So this is an excerpt of his letter talking about the equation. It's in Latin, problema. And then you can see the notation was already very similar. I bet you could understand it if it was translated into English. But you can see the q of x, y to the n, and so on. Okay. And then the reason why it's special, first of all, it's special to have a differential equation with the closed form solution. And it's nonlinear too. Wait, is it nonlinear? Yes, it's nonlinear because this n is a power, not a derivative. Right, okay, so this n is a power, not a derivative. It's not the nth derivative of y. It's y raised to the nth power. So that's what makes it nonlinear. So that's what makes it special, because it's a nonlinear equation with a closed form solution. All right, and then the other thing that makes it special is a special case of this equation is called a logistic differential equation. Logistic equations are used to model population growth subjected to constraints, subject to constraints. I know you know how to model population growth without constraints, like if something increases by 1% each year or whatever. But in reality, there's usually constraints. Constraints come in the form of limited resources, like area of spread, food, and then conflicting populations. So like a predator population and so on. If you want to model populations subjected to whose growth is subject to constraints, you get a type of a Bernoulli equation, which is another reason why it's useful to know how to solve those. Okay. All right. So let's take a look at a Bernoulli equation. Y prime plus p of x times y equals q of x times y to the nth. Okay, this is a power. I know on the slide where I defined linear equations, the n in the superscript was meant as a derivative, but nth derivative, but this is actually a power. Okay, so this is the logic behind solving these. If there was no this y to the n term, this would be a linear equation, and I know how to solve linear equations with integrating factors. So the first step is you start with your Bernoulli equation, you divide everybody by y to the n. Okay, you divide everybody by y to the n. So here you get q of x, here you get y to the negative n times y prime. There's a y here already, so you get p of x times y raised to 1 minus n power. And then this almost looks like a linear equation. The only difference is a linear equation just has a derivative of a function here. Okay, not a derivative of a function, times something. So you guessed it, what we're going to do is we're going to introduce a substitution. And you can play around with it a little bit. What substitution would you introduce? So this is a derivative of a function times a function of x times the function. And you'd arrive at the fact that if you let v equal y raised to 1 minus n, then v prime is, just apply the power rule, 1 minus n times y to the negative n times y prime, because of the chain rule. You can perform the following substitution. Replace y to the negative n y prime with v prime times 1 divided by 1 minus n. And then remember, n is just a real number. So this is just a constant multiplier. Plus p of x times v equals q of x. So we're getting closer to it looking like a linear function, a linear differential equation. And then you can multiply each term by 1 minus n. So you get v prime, a derivative, plus remember 1 minus n is just a constant. A function of x times the function equals a function of x. So this is a linear differential equation and can be solved by introducing an integrating factor. So yes, so that's how you solve Bernoulli equation. You force them to look like differential equations by linear differential equations by introducing this substitution. All right, so let's look at an example. This is easier said than done, obviously. And then if you have like 10 different things of this, imagine memorizing them for a test. Yeah, it can get